Hmm. Hi everyone, my name is Avinash Swaminathan and I would be presenting our work on a preliminary exploration of GANs for Keyphrase Generation. This is a joint work done between MIDAS Labs IIIT Delhi and Bloomberg, New York. First, let us discuss what is the task of Keyphrase Generation. Keyphrase generation is the process of generating phrases from an input text or document that capture the most salient information about the input. For our work, the input is in the form of scientific abstracts. Consider the given abstract. Our main task is to train a model that can generate key phrases given this abstract as an input. So you can see clearly here the speech input speech interfaces are keywords of this abstract, which talks about a paper on the role of speech input in variable computing. There are two types of key phrases, extractive and abstractive. Extractive key phrases are the ones that can be extracted from the source text. So we see here that speech input is an extractive key phrases which is present in this source abstract. Abstractive key phrases are the ones that are not present in the source text, but they can be inferred from the context of the source text. So we can see that the abstract here is talking about the role of speech input in variable computing. So variable computer, even though it is not present in the source abstract, can be a keyword, key phrase. There are most of the original sequence-to-sequence models for key phrase generation have been trained using maximum likelihood estimation, or MLE. MLE trained models often generate text that is machine-like, unreadable, and suffers from exposure bias. However, in the past few years, the application of GANs in NLP tasks has been shown to overcome these problems. Wang and Lee in 2018 applied GANs to abstractive summarization and found the summaries to be human-like and diverse. Thus, we decided to replicate this success with the GANs in the task of key phrase generation. Our work mainly focuses on the use of GANs for generating key phrases and shows promising results in generating absent key phrases, while achieving similar performance on extractive key phrases as the state of the art. We also propose a new discriminator structure to evaluate the quality of key phrases generated by the generator and further fine tune it during the adversarial training process. However, training of GANs is not an easy task and we encountered several roadblocks on the way. Training of GANs is highly unstable due to the diminishing gradients and mode collapse problem. During the adversarial training process, it is impossible to backpropagate the loss of the entire GAN setup because of the sampling that is being done at the generator's end. We first weekly pre-train the generator using the maximum likelihood estimation or MLE on KP20K, a large key phrase generation corpus. Then we train the discriminator with samples from the corpus and the generator. The key phrase sequences from the corpus are treated as positive examples and the key phrase sequences from the generator are treated as negative examples while training the discriminator. Once the generator and discriminator are pre-trained, we train the generator and discriminator jointly in an adversarial fashion. The goal of the adversarial learning is to make sure that the generator maximizes the expected reward that the generated key phrase sequence attains from the discriminator. We repeat training of steps 2 and 3 till the model stops converging. This is the full framework and training setup which facilitates generative adversarial learning. First, we generate a key phrase sequence which is then passed on to the discriminator. During the discriminator training process, the output from the generator is treated as a fake key phrase sequence, while the key phrase sequence from the dataset is treated as a real one. We calculate the binary cross entropy loss and train the discriminator by backpropagating and minimizing this loss. During GAN training, we extract rewards of all generated key phrases from the discriminator and update the weights of the generator using policy gradients. We continue this process back and forth. The generator is a normal sequence-to-sequence encoder-decoder model with attention and copy mechanism to capture relevant portions of the source text. We use a generator model on CATSIC, a version of copy RNN that ensures that variable amount of key phrases are generated. Now let us look at the discriminator. The discriminator is based on two-level hierarchical attention to score the generated key phrases. In the first layer, we generate a custom embedding for every key phrase and word of the source text using a bidirectional GRU. Then we combine the embeddings of the keywords and the source text using attention to generate a context vector for each key phrase. The context vector for all key phrases is passed into a second by GRU, and the reward for a particular keyword is a sigmoidal output of the bidirectional GRU at the other end. This enables us to provide rewards for partially decoded sequences. In our experiments, we trained the model on a KP20K train set, validated it on the KP20K validation set, and tested on the standard inspect CRAPEVN NUS and KP20K datasets. We evaluate the model in terms of f1 at the rate of 5 and f1 at the rate of m scores for two different reward schemes. The two different reward schemes are GAN-MR and GAN-SR. In GAN-MR, we provide different rewards to each key phrase, and in GAN-SR, we provide a single reward to the entire key phrase sequence. Naturally, GAN-MR outperforms GAN-SR as it allows a diversity of rewards. First, let us have a look at the F1 scores for extractive key phrases. In some datasets, especially in NUS and KB20K, MLE models outperform our GAN model in generating extractive key phrases, but in the other datasets, the GAN model outperforms the MLE models. Now let us have a look at the F1 scores for abstractive key phrases. In most datasets, our GAN model outperforms state-of-the-art MLE models in generating abstractive key phrases. We also decided to conduct experiments to ascertain the effect of the discriminator structure on the training process. So we took three different models. The first model is GAN. In this model, we only use a normal LSTM as a discriminator. In GAN GRU, we eliminated the generation of a context vector and hierarchical attention from our discriminator, and GAN MR refers to our proposed multi-reward GAN model. As we see, GAN MR, our proposed model significantly outperforms all of these models. We also measure the key phrase diversity using the alpha NTCG metric and found out that the diversity of key phrases generated increases after GAN training, and our GAN model is better than the state-of-the-art MLE models at generating diverse key phrases. Now let us look at some examples of the generated text for GANs. In our first example, our GAN model improves over the MLE output by combining the key phrases image and registration, creating a new key phrase, image registration, thereby improving the F1 scores of the model. Second example, the GAN model removes the redundant key phrase, speech, and appoints a new word, background, to the keyword noise in order to generate a new keyword, background noise, which is also a ground truth keyword. Thus, we see that the generated keywords are more human-like and increase the F1 scores over MLE models. Thanks for attending the presentation.